Welcome to this explainer. Today, we're zooming in on the fascinating, honestly kind of magical world of the Fibonacci sequence. We're going to discover how a remarkably simple mathematical rule literally governs the beautiful structures of our natural world, our greatest artistic achievements, and yeah, even the cosmos itself. So if you've ever felt like there's a hidden order to the universe, well, you're absolutely right, and we're going to unpack exactly how it all works. We're going to kick things off with a pretty grand mystery. Seriously. Take a second to think about this. Why on earth do incredibly diverse things, like a tiny little pine cone you'd find in the woods and a massive sweeping spiral galaxy floating in the depths of space, why do they appear to share the exact same architectural blueprint? I mean, it sounds like pure science fiction, right? But this connection, it's not a coincidence. It's actually rooted in a highly specific, observable mathematical law that dictates how things grow and expand in our universe. Section 1. Nature's Hidden Secret Code. So, this hidden pattern is an incredible, recurring design you can find literally everywhere you look. We're talking nautilus shells, the spinning clouds of a massive hurricane, all the way down to the veggies in your grocery store. Just look really closely at this macro shot of an aloe plant. Notice how the leaves aren't just sprouting randomly. Instead, they form these stunning, tightly packed spirals that almost look, well, intentionally engineered. The edges curl inward, layering over one another in this very deliberate rhythmic pattern. The plant is following a precise mathematical formula, which is wild because it obviously doesn't own a calculator. Now compare that organic, fleshy plant shape to this geometric diagram of a golden spiral. You get this shape by drawing an arc through a series of increasingly larger squares. And man, this brilliantly illustrates the direct connection between the hard, abstract numbers of geometry and the organic growth of life. The curve of that aloe plant and the curve of this mathematical diagram are, for all intents and purposes, functionally identical. Section 2. Unlocking the Fibonacci sequence. To really grasp this connection, we've got to unlock the Fibonacci sequence itself. Now, it was named after the 12th century Italian mathematician Leonardo Bonacci. He actually published it in his 1202 book Liber Abaci to calculate rabbit populations, of all things. But actually, scratch that. It goes back even further. The sequence was known to Indian poets and musicians centuries prior as they studied rhythms and beats. To see this math in the real world, just take the number 13. It's not just a random or unlucky number. It's a very specific figure you'll frequently find if you pick up a pine cone from the forest floor and count the left and right spiraling scales from bottom to top. You're almost always going to hit a Fibonacci number there, like 8, 13, or 21. The math to reach these numbers is beautifully, elegantly simple. You generate the entire sequence just by adding the previous two numbers together. That's it. So you start with 0 and 1, add them, you get 1. Add 1 and 1, you get 2. Then 1 plus 2 is 3, 2 plus 3 is 5, and it just keeps building and escalating, right? 8, 13, 21, 34, 55, onwards into infinity. It's what we call a recursive sequence, meaning it constantly builds upon its own immediate past to create its future. Section 3, the efficiency of life. But let's pause here and ask the obvious question. Flowers definitely don't use graph paper. So why on earth does a flower care about 12th century math? Well, the absolutely crucial point here is efficiency. Think about it. If a sunflower grew its seeds in straight, linear lines radiating from the center, it would leave loads of empty, wasted space as the flower head expands. And in nature, wasted space is wasted energy. But spiral growth, dictated by our sequence, allows the plant to pack seeds as tightly as possible without any overlapping. By growing seeds at a very specific angle away from the previous one, the sunflower maximizes its surface area. So it's an evolutionary survival tool. It's not just a pretty design. This biological drive for maximum efficiency is exactly why we consistently see these specific sequence numbers popping up all over the garden, or even the protostyle. For instance, irises naturally have 3 petals. Buttercups and wild roses, they feature 5. If you slice a banana, you'll see 3 seed sections, and if you cut an apple horizontally, you're going to find a beautiful 5-pointed star marking its seed sections. Nature just naturally defaults to these numbers because they literally represent the path of least resistance for biological growth. Section 4, the golden ratio. Okay, so as the Fibonacci numbers get larger and larger, something really cool happens. If you take any number in the sequence and divide it by the preceding number, say 55 divided by 34, you get closer and closer to a very special figure, 1.618. This is the famous golden ratio, or phi. Because it's an irrational number, meaning it can't be written as a simple fraction, it serves as the absolute perfect degree of turn to prevent overlapping in natural growth. If a plant turned at a simple fraction, like a quarter, the seeds would just stack directly on top of each other after 4 turns, right? The golden ratio ensures these endless, non-overlapping spirals. Now, quick caveat, we do need to bust a myth here. Nature isn't always rigidly mathematically perfect. Variations definitely happen, but the sequence emerges so incredibly often simply because it's so practical and efficient for survival. Section 5. Art, Music, and Design. What's truly captivating about all this is that humans have actually subconsciously recognized the aesthetic harmony of this natural sequence for centuries. We've taken this biological blueprint and harnessed it way beyond mathematics, weaving it right into our greatest cultural achievements. The sequence just echoes throughout human creativity. We see it defining the structural proportions of Mozart's piano sonatas, where the number of bars in the development section divided by the exposition closely mirrors that 1.618 ratio. We see it anchoring visual masterpieces by Leonardo da Vinci and Salvador Dali, whose compositions use the golden spiral to perfectly draw your eye to a central focal point. You can even find these spirals carved into ancient Chinese jade bee discs or painted on Japanese insero boxes. Heck, even today, modern graphic designers rely on the golden ratio to establish pleasing typography grids and layout structures for the websites we use every day. It even inspires structural literature, which is amazing. Take a look at this beautiful form of poetry known as a fib poem. The syllable count of every single line corresponds exactly to the mathematical sequence. Just listen to the rhythm as it builds. Trees, in, the woods, standing tall, waving their green leaves, catching and filtering sunlight. It's this brilliant creative restriction that literally mimics the structure of the trees the poem is describing. How cool is that? Section 6. Math in the Natural World. As we bridge this incredible gap between left-brain mathematical logic and right-brain artistic expression, we inevitably return to the grandest canvas of them all, the natural universe around us. What started as a 12th century thought experiment about the breeding calculations of a hypothetical rabbit population, well, it scales all the way up and all the way down. From the logarithmic protective spirals of a tiny nautilus shell in the ocean, to the massive, sweeping, majestic arms of a spiral galaxy light years across, it's abundantly clear that mathematics is intimately, permanently woven into the very fabric of reality. It's not just something we invented, it's something we discovered. So, as the mathematical overlays and grids fade into the breathtaking vastness of space, we really have to ask ourselves an inspiring question. If a simple, additive rule of numbers governs both a humble pine cone in your backyard and the spin of a massive galaxy in the cosmos, what other breathtaking codes are out there, just waiting to be uncovered? Keep your eyes open, folks. Look for the spirals. Thanks so much for joining me on this explainer, and keep exploring.